Thank you for joining this session. As you know, my name is Dr. Payal Bhattacharya. I am a current PhD graduate from the University of Missouri at Columbia in the US, and I'm currently positioned as a senior optical thin film engineer and laser metrologist at MKS Instruments. Um, Newport Corporation location at Irvine, California, and we work closely with our sister concern, Spectrophysics, whose lasers I have used in my PhD project, and I will be talking about. My presentation this morning is titled Ultrafast Nonlinear Optical Probing, Enabling Insights into Organic Semiconductors. A previous speaker in this session was also talking about organic semiconductors, so the audience probably has some idea already. Before I go into my presentation, I would like to share my acknowledgments to my PhD team, to my PhD advisor, Dr. Suchi Guha, and Dr. Ping Yu, my PhD co-advisor, as well as colleagues and collaborators from the University of Missouri, Columbia, from various departments, as well as Texas A&M at Qatar. The project was completely supported by NSF funding, as you can see on the screen. I really appreciate this opportunity, and now I will go into my research. Now, as you know, organic semiconductors is a unique class of organic materials that emerged in the late 1970s that owe their semiconducting properties to the conjugation of alternating double and single bonds, which leads to the formation of delocalized pi electron clouds above and below the molecular planes, which gives them various unique physical properties such as lightweight and mechanical flexibility, which finds them application in flexible electronics such as bendable displays, as well as high photosensitivity and transparency help them find application in transparent electronics such as transparent window panes that are also equipped to be solar cells. To some extent, they can be made non-toxic and sustainable and find various applications in biomedicine research such as retina chips and other applications that are popular at the current time. Along with that, these materials have a substantial ease of fabrication at low temperature or room temperature processing, which reduces the production costs to a great extent, which is what adds to the appeal of such materials. One of the key cornerstone in organic semiconductor based research is organic field effect transistors, which, as the name suggests, are three terminal devices with gate, source, and drain electrodes, as you can see in the image, where the semiconducting material is separated from the gate electrode using a layer of dielectric material. Unlike its inorganic counterpart, excuse me, I have a bout of flu, very unfortunate timing. However, going back to the presentation, unlike its inorganic counterpart, organic field effect transistors, they operate in what is known as the accumulation regime, where the application of a perpendicular gate source voltage leads to the accumulation of charges at the semiconductor dielectric interface, as you can see in this image, which is heavily dependent on the energy barrier between the work function of the metallic contacts, as you can see here, as well as the HOMO or LUMO level of the semiconductor, depending on whether the semiconductor used is P-type or N-type. Once the accumulation layer is formed, the application of a in-plane drain source voltage then leads to the transport of the charges across the channel, leading to a drain source current. According to popular industry predictions, we are right at the onset of mass market ramp of these organic semiconductor-based technologies. However, there are several barriers in research and development of such systems, where number one, of course, is low performance compared to their inorganic counterpart in terms of low carrier mobility and speed. There are certain limitations found in the traditional IV or electrical characterization of such devices, where the cause of ineffective probing often leads from high contact resistance at the non-ohmic contacts between the metallic contacts and the organic semiconductor found in these materials, as well as a higher density of trapped charge states both in the bulk and interface of these materials, which leads us to underestimate the transport parameters or transport properties of such devices. Thus, to enable us to understand the transport mechanism better, which would help us to improve performance and harness the full potential of organic semiconductor based research, the necessity for alternative characterization techniques was felt. One of the major questions faced by this industry is why would the same semiconductor behave differently in different transistors? What I mean by this is when the same semiconductor is placed in different device architectures or when used with different dielectric materials, the semiconductor has been seen to um, act differently. At this time, time resolved electric field induced second harmonic generation has emerged as an important technique for understanding intrinsic transport parameters in such devices while enabling us to do real time measurements of carrier dynamics and revealing the real impact of the semiconductor dielectric interface in these devices. To give a brief overview, electric field induced second harmonic generation, unlike second harmonic generation, is a third order nonlinear optical phenomena, which really arises from the coupling of from the application of an electric field, which leads to the orientation of the molecular dipoles, where the applied electric field couples with the dipole moment of the molecular dipoles, thus breaking the symmetry of the material, which enables the system to be SHG active. In our case, while using the transistors, the application of the in-plane drain source voltage in the parallel direction as shown in the diagram leads to the symmetry breaking phenomena, which induces dipole moment in the molecular level, which couples with the applied electric field, thus rendering the system SHG active. In terms of time resolved measurements, the electrical pulses used for operation of such devices are synchronized with the probing laser pulse, and different delay times are used for studying time resolved uh, parameters. Excuse me, I cough. Here is a schematic of our femtosecond pulsed laser system that has been used for the TR or time resolved EFISH imaging of such devices. Here we have used Spectrophysics' ultrafast laser femtosecond laser product line, their Spitfire Ace product line, along with an OPA, which helps us to which was used for the wavelength conversion between 1120 nanometer and 2 micrometer. The system is equipped with a group velocity dispersion or GVD compensation system, as you can see in the inset here, using a prism pair to compensate for any group velocity dispersion introduced in the broadband laser system, in the broadband laser source while going through various optics, um, as well as the electrical circuitry of this setup helps us to do the time resolved measurements, as I mentioned earlier. The, um, the setup is equipped for SHG imaging as well as spectroscopy, which is not shown in the diagram. And the imaging as well as spectroscopy is done in situ, while the devices shown here are in operation. I would like to discuss a few results that we have obtained using this system. Here in this example, we have discussed some results when the devices are in their operational regime, which means that a device shown as such using a DPP-DTT donor acceptor copolymer based semiconductor, when operated in its saturation regime, yields a saturation mobility from electrical characterization of about of the order of 10 to the power negative 2 centimeters square per volt second. However, the right-hand side panel on the top here shows time-resolved EFISH imaging from the same device from the channel region. As you can see, the channel from there's a top view of the channel between the source and drain electrodes. When under saturation regime operation, when images are second harmonic generation images are taken with various delay time corresponding to the transit time of the charge carriers, a movement of the polarization wavefront can be seen across the channel, which gives us excuse me, which gives us a sense of their mobility when we treat the such FETs as a Maxwell-Wagner element. You can see the intensity of the polarization peak moving across the channel region as a function of position as shown here. Of course, there are small peaks closer to the source and drain visible as well, where the symmetry is broken due to a difference in the layers. And thus we see a little bit of SHG activity. However, the most interesting peaks in this case are the ones that correspond to the polarization wavefront that moves across the channel as we let the motion of the charge carriers happen over their entire transit time. Uh, on application of the Maxwell-Wagner model, the slope of the position square versus delay time then gives us a sense of the intrinsic carrier mobility of these devices free from contact resistance or trap interface trap state density. And it has been found from our studies that the carrier mobility found from EFISH measurements were almost 22 times higher compared to what when measured using IV characterization. Here on the table at the bottom of the slide shows a few other examples of semiconductor FETs where the effect of the dielectric constant as well as the high contact resistance can be seen directly translated into the underestimation of the electrical um, carrier mobilities, where the EFISH carrier mobilities then give us a more intrinsic values. Apart from the operational regime, various other information can be extracted, of which I will discuss a couple here. For example, the application of a gate source voltage, as I mentioned earlier, leads to the formation of accumulation region. However, interface charging effect can be studied in the absence of drain source voltage, which leads to the absence of any drift voltage leading to the transport of the carriers across the channel. What happens here is because the drain and source electrodes are both maintained at a zero potential, they're essentially the same electrode, and the transport of charge carriers really happen in terms of injection through the dielectric layer into the interface between the semiconductor and the dielectric. If you look at the images here, as you can see, going with the transit time, you can see the accumulation of the charge carriers closer to the drain and source electrode, and then eventually the entire accumulation region being formed uniformly from both sides till it is completely uh, region is completely formed. And it has been found from Maxwell-Wagner model that the interface carrier mobility is about half of that obtained from operational mobility. Using these results, we can understand the rate at which the accumulation layer is formed in various FETs and the effect of the uh, uh, density of interface trap charges, which leads to the alteration of the rate of formation of accumulation layer, as well as the direct impact of the dielectric semiconductor interface at this point. We have repeated, as usual, the same experiment with various combinations of semiconductor and dielectrics and has received expected results. Moreover, In terms of other non-operational regime applications, the Laplace field contribution, or the contribution due to the applied electric field, can be directly mapped from e-fish imaging, as you can see here. And this is particularly useful in deconvolution of the Laplace field contribution from when we operate them in the operational regime, which is supposed to be a combination of the Laplace field contribution due to the applied field and the Poisson field contribution due to the motion of the electrical charges. So that again helps us in the deconvolution of the Laplace field contribution from the total contribution. Thus, in summary, there are several advantages of the TRE fish probing of the OFET versus the traditional IV characterization that I have mentioned here today, where number one is the direct visualization of the carrier dynamics in the channel region of these transistors enable us to calculate trap-free and contact-free transport parameters. Moreover, by altering the interface interfaces of the um, semiconductor dielectric, we can get a direct insight into the effect of the excuse me, the effect of the interface on such transport parameters, as well as direct visualization of the channel formation and electric field distribution in the channel region also enables us to understand the performance of such semiconductors, and thus help us to tap into the full potential of such systems when used in this technology. Thank you so much for your patience. I would love to take any questions at this time.